And we move to the next talk, which is by Jan Steinheimer.
Okay, thank you. Let me share screen. Okay. So I hope you can see it now.
You can see it, yeah.
Okay, so thank you very much. Thank you, the organizers, for inviting me and giving me the chance to present some of our recent results. So what I'm going to talk about is a little bit more phenomenological approach to the QCD equation of state at finite density, and basically trying to merge what we know from lattice QCD to what we know from neutron stars and nuclear matter, and try to come up with some equation of state which spans this whole region. So the motivation of this is, of course, I can show another phase diagram. Everybody shows a phase diagram in this session, I guess. And the one I'm showing is, well, first one, which I like very much, which has nothing to do with QCD, or at least not directly, which is the hydrogen phase diagram, which was calculated by already some years ago. And in the end, what we want to have is something which looks very similar, something which has the axis of temperature and the axis of density, and not so much in chemical potential. And when I talk about the phase diagram, it's not only critical endpoints and phase transitions, but it's also lines of constant pressure. Like, you can learn a lot about the features or the properties of a substance by also looking at isobaric lines and so on, as we will see later. And so on the right hand side, I show, just as an example, something which maybe we hope the phase diagram in temperature and then density could look like in the end. And this is from actually work which probably Veronica will talk about next. So this is not the model I'm going to talk about, but this is Veronica's result. And here you see, for example, you have some liquid gas coexistence region, and then you have maybe some hadron coexistence region, and then you have all kinds of phases which we don't know. But this is something we hope to achieve, and that's, so I kind of always like to show things in baryon density, not in chemical potential, because that helps you understand a little bit better what's going on. And so, as I said, we have a lot of constraints from lattice QCD for the thermodynamics. So this is something which we already know for quite some years. So this is the interaction measure of QCD. That is QCD at zero chemical potential or zero net density as function of temperature. And what we also have from lattice QCD is derivatives of the pressure with respect to the real chemical potentials, and also an expansion into imaginary chemical potentials. So this is basically what we get from lattice, and that's what we can use, at least when it comes to thermodynamics. So one thing we kind of looked at some time ago already is, how can we use these lattice data to kind of go into the finite density range? And as I said, one approach would be, okay, let's use the Fourier coefficients from some imaginary mu simulations input, because as you know, you can do lattice simulations at imaginary chemical potentials, but not at real ones. But if you use them, but you can connect both worlds. So what we did is here, basically, we said, well, why can't we write the density of QCD as a cluster expansion? This is kind of something people do in thermodynamics. So basically, your thermodynamic density is calculated as an expansion in these functions with some coefficients bk, and these bk are actually coefficients which have been measured on the lattice, at least up to the fourth order. And so the only thing you need to know is, if you now want to use these coefficients, and you can, from these coefficients, you can calculate basically the finite density coefficients, you kind of need almost unlimited number of these coefficients. So the first four will not cut it. However, what you can do, you can make some simple assumptions on how higher order coefficients are related to the first two. And that's basically this relation here, which is motivated by the Stefan-Boltzmann limit, because in the Stefan-Boltzmann limit, this is actually true. And from getting, so this way, you can basically try to calculate any kth order coefficient, and then use these to calculate the coefficients of the Taylor expansion in the real chemical potential axis. And if you do this, again, remember, this is just a very simplified, assuming the simplified relation, then you actually get something which is quite well describing the lattice data, which have also been measured in the real direction, but only up to a certain order. So basically the lattice is always these colored bars here, and the stars are what you would get if you take the lattice data for the imaginary chemical potential and then calculate this expansion coefficients. And so that it works quite nicely for the second and fourth order, and for the sixth order it also works rather nicely. And then you can make some predictions of what happens at higher orders of these susceptibilities. And so if you do this, and then what you find is that that you can expand your pressure in terms of real chemical potential. However, you can only expand it to a certain radius of convergence, right? Because every expansion has this radius of convergence. And in this particular case, the radius of convergence is always something like pi. And that's because we know that in the imaginary plane of chemical potential, there is a divergence along the imaginary part, which is mu b over t equals pi. That basically sets the boundary of how far you can go in your expansion business. And this is kind of a hard boundary. So if there's a it doesn't say that there's a critical point at pi. It just means that if it's beyond that, you are always limited by this divergence in the imaginary, in the complex plane. So of course, something similar was also done taking only the expansion coefficients chi in the real plane. So basically, as I said before, you can expand your pressure in terms of these coefficients chi, and then you can try to calculate these coefficients from lattice, and then you just plug them in and see how far you get. And this was done actually already some years ago, as you can see here. So what people there did, they took the lattice data and they expanded the density in terms of mu b over t. And what they found, okay, some artifacts appear also if you take lattice data which you have up to a certain order of chi. Artifacts appear about also mu b over t roughly 2.5 or 3, always hard to say. And they also estimated the radius of convergence, which is about mu over t about 3. So always you get this number 3. And I mean, one interesting result was always here that if you go to high temperature, then higher orders of mu b over t or of chi didn't really contribute that much anymore, or higher orders than 4, which kind of tells you that, which is, of course, must be true in the Stefan-Boltzmann limit, because there you don't have any orders of, the pressure only depends on the highest order on mu to the 4th, but you already get such behavior already much lower than that, which kind of tells you that there shouldn't be too much of quark repulsion for at least free quarks, but this is a whole different story. Anyway, so the question is, why is there this breakdown at mu over t roughly 3 in all these things? And to kind of understand this a little bit, from the thermodynamic point, what I plotted here is again lines of constant pressure in the phases of t and rho from a model which I will explain next. But this is just a model which includes, let's say, baryons and mesons and quarks and gluons. And this is actually a rather general result. So you can also look at the same plot for just a hadron resonance case, or maybe just a very simple quark model. And what you see is that as your chemical potential over t approaches 3 or pi or whatever, yeah, you see that these isobaric lines go from horizontal to vertical lines. And what does that mean? That basically means that the pressure at the left side of this curve is dominated by your bosonic or mesonic and gluonic degrees of freedom, while as you go beyond that, your baryons or your net baryons actually start playing a huge role. That's why, at least my hunch would be, well, all these first principle calculations seem to fail once the contributions from the fermic or net fermions becomes larger than just a small perturbation. And therefore you kind of have to find different methods on how to describe this part of the phase diagram. So we heard before there are some other approaches, and of course let me talk a little bit also now on constraints we have at t equals 0. And here we have actually guidance from neutron star mass measurements. So as we all know, yeah, you can try to measure the mass and the radius of neutron stars, and you can relate this then to the equation of state of neutron matter and dense matter at t equals 0. However, there's a lot of models, as you can see, and there was not much constraints. Recently, there was a more systematic study where people try to, take nuclear matter constraint seriously, take peak QCD constraint seriously, and then interpolate in between and try to this way get the pressure as function of energy density, or at least a likely pressure as function of energy density. And also there was some work where people tried to extract from very few measurements of mass, combined measurements of mass and radius, to extract kind of something like a most likely equation of state at t equals 0. And this is actually a good already constraint. What we are still missing, and I made this little drawing here, is basically, so we have some constraints at small baryon density and at high temperature, and we have constraints at t equals 0. What we are kind of missing is this interesting area here, where we have to rely on model or other approaches. And so what we try to do is, our strategy is, well, let's try a phenomenological approach. And what could we do instead of, can we have an alternative approach to doing this instead of just taking lattice data? So what we did is we tried to design an effective model that matched with QCD at low chemical potential, a neutron star and nuclear matter properties at high density. Then see how both kind of merge into each other, both regimes. And then we want, of course, what you want to do, you want to employ this model for heavy ion collisions as well as neutron star merges and see whether they give reasonable results or not. And this, of course, needs, for this, we need to find a consistent description for both. Yeah, and so the example I'm going to talk about today is this the chiral mean field model. So it's a SU3 flavor chiral mean field model. And it's based on several concepts. One is that chiral symmetry via hadrons is realized through parity doubling. That means that you have a ground state baryon, and this ground state baryon has a parity partner, which is basically a baryonic state with the same quantum number except opposite parity. And then the appearance of chiral symmetry then is manifested not in the dropping or disappearance of the mass of the baryon or the nucleon, but in actually the degeneracy of these two states. So both states have the same mass, but they have different, but it's non-zero. Right, and there were some. So this idea was put forward about, I don't know, probably more than 20 years ago, and we extended this to 3 flavor. And then what you have basically an effective mass for your baryons, which now depends on several coupling constants, and you have, of course, some interaction potentials for your chiral fields, which has a lot of parameters, and you kind of try to fix these parameters in order to describe the masses, the known masses of the baryons, and the nuclear matter properties. Right? And then you already can fix a lot of these parameters because you have another, because you also try to take into account the constraints from neutron star observations. And if you do this, then you basically can nicely describe your neutron star matter. No, I jumped something, sorry. So, but what you also wanted to do is have some kind of deconfinement effect, because right now that would only describe hadronic matter. What we also want to do, we want to describe then the transition from hadrons to a gas of free quarks and gluons. And then to achieve this, we included a model which is basically similar to the PNGL model, where you have the thermal contribution from the quarks entering through this sum where the quarks couple to some mean field description of the Polyakov loop, and this Polyakov loop is then constrained by this Polyakov loop potential. So this is again a mean field description for this, and what you get then, and again you get a new set of parameters basically, and you tune these parameters for to describe lattice QCD data at 0 chemical potential. So that's how you fit your quark world. And if you do this, then you get kind of a natural transition from hadrons to quarks, because as the quarks come in, they will suppress the hadrons, as hadrons have a finite volume, and therefore will be suppressed by these appearing point-like particles. And that's what you see down here. So basically, this is at t equals 0, the densities of the different particle species. So you start off with something which is dominated, of course, by neutrons, for example, for a neutron star, and then eventually, as the quarks set in, they get suppressed. Of course, there's some area of coexistence, and then the quarks in the end dominate your system. Now, if you take this model, you can calculate the speed of sound, and you can calculate the mass radius diagram. So the mass radius diagram is in agreement with what we know from mass radius constraints. That's good, but we can also look at what is the speed of sound as function of density, which is something like the equation of state at 0 temperature. And here you can see it actually has a very non-trivial structure. So there's a lot of particles appearing and disappearing, and that gives you all kind of kinks in the speed of sound. And there's also very small phase transition at 0 temperature, at about 4 or 5 times saturation density. And I will show you a little bit later more about this. There is more what you can do with this, because you can apply also this for not only for cold compact star, but also this might be interesting for effects in supernova and the cooling curve, because right now what people haven't really studied much except for this one paper is what is the role of these parity partners in warm neutron stars, and how do they relate to the cooling curve. There is a small caveat, of course. As I said, it's an effective model, so you have a lot of parameters which you can fix. And in principle, you have a lot of hadronic degrees of freedom, which could all have a different coupling strength. So what we try to suggest is, of course, you can try to fix all these couplings, because you also have an infinite amount of observations, which are these which are the charged susceptibilities from the lattice QCD. And that's what we tried here. And what we saw there is that, of course, that for example, the baryon correlation and the quark, the charge correlation and the baryon strangers correlation, they all depend to a certain degree on the relative interactions between the hadrons. And if we kind of tune all these interactions to describe these data, then in the end, it turns out you get slightly different thermodynamics at finite density. However, the general features of the model, they actually are very insensitive to all these details on the different parameters, and that was kind of a nice result. So which brings me back to this plot. So I've shown it before, and this is now again the resulting phase structure of this model. And what you see here down here in density is this, what we all know as the nuclear liquid gas transition. So this is nicely described. But then again, the same model, as you increase the density, there's another transition which occurs, and that's basically where the parity partners and they become degenerate. So that is what we would call the chiral transition. And what you can see, the critical point of this one is not very high, right? And that's basically because already the liquid gas transition, you have a jump to a very finite density, and then as you slowly keep increasing density, the gap between the hadronic phase and the quark phase and the deconfined and the chiral symmetric phase becomes smaller and smaller, so the phase transition also becomes weaker. And this is basically just a result of introducing this nuclear matter phase in here. So now this equation of state enables us to treat heavy ion collisions and neutron star mergers on the same footing, which is nice, because now we can use this in, for example, fluid dynamics, which can which can be basically used. You can use any model for the equation of state in hydrodynamics, plug it in, and then see what happens. So in which scenarios do we see effect from a phase transition in these simulations, or which violates our constraints? Again, of course, there's more constraints possible. As we've heard before, there's an infinite number of constraints, and one has to kind of think about which ones to take into account, and you probably won't be able to satisfy all of them. So, but what's the data situation in heavy ion collisions? So in short, what they usually really measure in heavy ion collisions are correlations and fluctuations in momentum space. And the downside of this that you have a lot of freeze out, rescattering, which wash out all these signals from the equation of states you put in. So you really need to implement this in a fully dynamical description from pre-equilibrium to freeze out, and that's very cumbersome. So you don't really like this. However, what you can do, you can look at this very simplified picture of a heavy ion collision I show here. So you basically have a soup of boiling matter, and then hopefully find some observable which is sensitive to that. And that's, for example, would be the dilepton emission from these heavy ion collisions. And that is a process which is much more sensitive to the medium in which it takes place, and you don't have to worry so much about non-equilibrium effects. And what we showed here is, like, if you take two different parameterizations of this chiral mean field model, in the left-hand side, the one which we fitted to all the lattice data and the neutron star data on the right-hand side, one where you just artificially introduce the phase transition, then you see already the kind of the evolution in the T and rho diagram of these systems at fair energies is very different, and this actually translates into a huge effect in the produced dilepton rate. So you basically, this basically shows the enhancements of the dilepton rate with respect to when you have a phase transition with respect to no phase transition. So you can see all these things if you put them into the simulations, and you have to find the right observable which is not so sensitive on the non-equilibrium stuff. So in the final minute, I would just want to say what we are also doing is now trying to find out what is the area of the phase diagram which is tested by these binary neutron star mergers, and what is the overlap with heavy ion collisions here. So what I show here is only the simulation for a heavy ion collision. So you can see for, let's say, a heavy ion collision at 600 MeV per nucleon bombarding energy, which is really low, to, let's say, lower GSI energy, you see you reach densities of about 2 times saturation densities and temperatures about up to 40 MeV. And on the right-hand side, you basically see some snapshots from the time evolution from our hydro simulation. And what I cannot show it to you, but I can tell you already that the first results show that these binary neutron star merger systems, they create an entropy of a baryon which is 2 to 3, which is actually very comparable to these heavy ion collisions at less than 1 AGeV. So you really have to go to very high density, not very high density, but very intermediate or low temperatures to really compare this. So to summarize, I would say lattice QCD is directly useful up to mu b over T roughly 3. After that, fermions really become the dominant degrees of freedom for your thermodynamics. Your neutron stars properties constrain the T equals 0 thermodynamics, and at least in our model studies, when you try to reconcile both these constraints, you always get a very low critical endpoint. Of course, I would be happy to see a higher one which reconciles also both these properties. And again, what you need is combined complex models. You want to describe the matter at low energy heavy ion collisions and neutron star mergers. We should take all these constraints seriously, and basically neutron star mergers and low energy heavy ion collisions probe these complementary regions of the QCD phase diagram, which is why we should try to treat both on the same footing and maybe learn something from this. Okay, so with this, I'm finished, and thank you for your attention.
Thanks, Jan. Very well, very nice talk, and very well kept in time as well. Are there any questions? Yes, there are. Anirban, first one.
Yeah, thank you. So in the hybrid modeling, so how do you switch from the hadronic to the quark part in between?
Okay, yeah, that was pretty quick. So we don't switch by hand. So actually, that's the reason why we introduced the finite size for the hadrons. And if you do this, then basically your hadrons get thermodynamically suppressed once particles appear, or point-like particles appear, which have a finite pressure. So if you look at this excluded volume description of hadrons, basically your chemical potential of the hadrons gets a term which is minus the pressure of all other particles times the volume of the hadron. Mm-hmm. So as soon as basically the quark pressure and the gluon pressure increases, the hadrons get automatically suppressed. So that's kind of a switching mechanism here.
Okay, thank you.
And then Petrov has a question.
Yeah, my question is, when you consider, for example, a heavy ion collision, according to you, which time every of phases you mentioned in your talk can exist?
Sorry, which type of phases, or what was the question?
Which time? How much time it takes, for example, in the heavy ion collision, for any one or another phase to arise, to exist?
Well, okay, so the lifetime of the heavy ion collisions at these low energies is, on the order of 10 to 30 Fermi over C. Mm-hmm. And so usually the first 5 to 10 Fermi over C is where your stuff still starts, it comes streaming in and it's piling up. And so maybe after 10 Fermi over C, your system could be considered, at least if it is like in best case scenario, that's the time where you can assume it to be equilibrated, at least locally, and then it lives for, let's say, another 5 to 10 Fermi over C.
if there exists some kind of feeling about relaxation times.
Well, that you really, okay. Well, that depends a lot on your microscopic theory, I would say. And this is something maybe I wouldn't want to answer here, because it really, so you can do a lot of model simulations in microscopic theory, and they give you then some result on how long it takes for your system to relax into something which resembles equilibrium. But again, it depends a little bit on what observables you're looking at. For some observables, you probably don't need to be fully equilibrated, so it looks like you're in equilibrium, and some it does. So it's
Okay, good. Thank you.
It's hard to say.
Okay, I have a question myself. At some part, I thought you said that there's a limitation from being mu over t being less than pi for many models. But then on the final slide, you just mentioned lattice QCD. So I'm a bit confused. Maybe you can repeat.
Well, okay. Many models. I mean, like, for example, if I show, wait, I have it. Do I have it? This cluster expansion model, for example. This is also a model, but it uses lattice data as input. But it's also clearly constrained by things that are happening in the imaginary or in the complex plane.
Mm-hmm.
So I cannot take this model and expand it beyond this point, even though it's just a model.
Okay, so in the complex plane, you mean because of the Robert-Weiss singularity?
Exactly, because that kind of is a hard boundary for all this stuff. Even though it doesn't mean that there's a critical point, it just means if there is one, if there is one which is beyond mu b over t equals pi, then you wouldn't see it in this kind of approach.
Okay. So maybe there's something for the discussion session yet, because every model that faithfully describes QCD should be sensitive to the Robert-Weiss transition.
Yes.
So let's
yeah, okay, if you have a model, but the point is QCD, you cannot calculate it directly at real chemical potential. If you have a model which you can calculate directly at real chemical potential, you're not worried about any radius of convergence.
Right. Okay. Fritjof, you want to comment?
I have to unmute. Sorry. Yeah, concerning this discussion about pi, I found it interesting that the pi usually comes out of arguments about Matsubara frequencies and so on. But the way you related it to physical effects, the pi seems to be more a 3, which is related to the baryon mass, saying that the relevant temperature range is about 1/3 of the baryon mass.
That's interesting. I mean, in this CEM expansion, it's clearly the Robert-Weiss transition which is limiting it, right? So that's because we did, that was the finding here. On the other hand, I kind of pointed out that is also a point where we would expect the thermodynamic contribution from the fermions or for the net fermions to dominate. Whether this is actually the same thing or which it's related, I don't really know. So is there something which relates both? I'm not saying it's the same thing, but it's at least interesting that both happens at the same, approximately the same mu b over t.
Yeah, I think we should discuss this more in the discussion session, because the Robert-Weiss is also not the Matsubara frequency. Huh? It's the because it's a phase. Okay, let's discuss it in the discussion session. So thanks, Jan.